All right, we're going to continue on here, chapter 18, I think. So we're talking about nuclear chemistry last time, and unlike regular chemistry, nuclear chemistry is really all about really the protons, the neutrons, sort of what is happening inside the atom's nucleus. And one of the major differences, as we talked about, between a nuclear reaction and a chemical reaction is that fact that protons are getting converted, for example, to neutrons, neutrons to protons. So unlike in a chemical reaction where we do have sort of the conservation of elements on each side of the arrow, in a nuclear reaction, we actually make new elements and stuff on the other side of the arrow. It's just square goes to a circle, I guess, in that particular case. So we talked about some major sort of particles that are very common in nuclear chemistry. We have our alpha particle, which is a very popular, 4 and 2. Or sometimes people will use the helium as the symbol. We also had beta particles, which is also like an electron there. We also had positron particles, which again does pretty much use the same sort of symbols there as our beta particles, but it is +1. We also have protons, uh, which again is kind of normal type thing. Neutrons as well. Are also some very common ones. So these are very common particles that we see. Because we do not have conservation of sort of the elements when we have a nuclear reaction, when we go to balance nuclear equations, there's basically two things that we look for on each side of the equation. And that is when you add up all the mass numbers on the left-hand side of the equation, they do need to equal all the mass numbers on the right-hand side of the equation, and vice versa there on the bottom. All the atomic numbers on the left-hand side of the equation does need to equal all the atomic numbers there on the right-hand side of the equation. Remember that if you are sort of missing an element or trying to figure out maybe what was formed as a result of this sort of reaction, it is the atomic number, which is the number of protons that you can find on the periodic table, that will help you figure out what is sort of the missing element. Remember, it could also be a missing particle. So if you have kind of a weird atomic number, and then you can also figure out the mass number that's missing. We talked about as well stability, and one of the big things that we looked at in terms of stability is the N to Z ratio, or really the neutron to proton ratio. And that ratio tells us about stability. And there is sort of this valley of stability or this belt of stability where our ratios of N to Z, for example, is 1 for 1 through 20, like 20 to 40 is like 1.25 and so forth. And if you sort of hit that ratio, you do have sort of a stable nuclide. If not, you may be too high. And if you're too high, you kind of need to bring everybody down. And the way that we do that is a beta decay process will occur. Now, if your ratio is too low, you need to kind of bring it back towards that valley of stability. And remember that you could do either an electron capture or a positron emission. And as we saw last time, regardless of which one you do there, the electron capture or the positron emission, it will basically end up in the same sort of element that's formed as a result of that. We also saw some other things that we looked at in terms of stability. Sort of the best situation really for sort of nuclides is when you have positive protons and, or sorry, not very positive, even protons and even numbers of neutrons. Sort of even is the best situation. The worst situation in terms of stability is when you usually have sort of odd and odd in terms of protons and neutrons. There's only like 5, I think we saw on that table or something like that, that is sort of stable. We finished up talking about sort of a decay series. And a decay series is just a bunch of radioactive emissions and decays happening where the product of the first decay process becomes the reactant of the second, product of the second becomes the reactant of the third, and you can do that. And we saw kind of two ways that you could do it. One is just basically just do a balancing nuclear equation for each of the decay processes, again using the product as the reactant to start with on the next one. The other one that you could do as well, if it's all alpha and beta type decays happening, for every alpha decay, you could subtract 4 from the mass number and 2 from the atomic number. And for every beta decay, you could add 1 to the atomic number. So if you're maybe just interested in what you get at the end of maybe it's just a series of alpha and beta sort of decays, you can kind of just keep track of it, kind of do the addition and subtraction. Or if you kind of want to see each one after each step, you could just do the reactions to do so. Any questions on any of that stuff there we talked about last time? All right, so I believe this is where we left off. So we're going to talk about kinetics, which you might have talked about there in 200A. Kinetics and radioactive decay. As you may remember from kinetics, there's like first order, second order, zero order type reactions. All radioactive decay follows basically first order kinetics. So first order kinetics is basically what happens in radioactive decay. And although there are some different sort of symbols here that we see on this page, it's really the same formulas that you can use for first order kinetics. They just sometimes will use some different symbols because it's radioactive decay. What that basically means is if you remember for first order, you had sort of an integrated rate law of the natural log of A is equal to the natural log of A naught minus KT. Here in sort of nuclear chemistry, instead of A, they use N to represent nuclide, and natural log of N naught minus. And sometimes instead of K, true sort of nuclear guys will sometimes use the lambda symbol to represent the decay constant. And here K is the decay constant instead of the rate constant. So this is the decay constant. And K or lambda is sometimes used for it. It's really the same thing. Although in kinetics, most of the time when we did go into those equations, we did go in with molarity. So one of the different things that we see in sort of radioactive decay and using kinetics is you pretty much could be any unit you could go into there with. So you could do like grams of grams, you could do milligrams of milligrams, as long as they're really the same units. Doesn't necessarily have to be molarity. In addition, you could also do, which is very common as well, radioactive sort of counts per minute or radioactive decay, counts per minute, counts per second, something like that. So you could do some type of decay rate in there as well. In addition, this is the half-life equation. The half-life is equal to the natural log of 2 divided by the decay constant, natural log 2 on your calculator, 0.693. That's where that number comes from. Is this, is that. And it's over the decay constant. So you can, again, like I said, use rates as well, and you use the half-life. The half-life is the time it takes for half of whatever you started with to basically go away. So if you started with 10, you got 5. After 5, you got 2.5. After that, I need a calculator, but you keep dividing by 2, basically. After about 10 or so half-lives, most of it's pretty much gone at that particular point. And these are, again, some of our integrated rate laws and 2 graphs that are very important in sort of first order kinetics. Once again, this is the same as the natural log of A is equal to the natural log of A naught minus KT. This is in kinetics, as you may remember, everything's about the straight line and drawing the best fit straight line. And if you rearrange this, it looks something like this, where this is in the form of y is equal to mx plus b. So on the y there, we have the natural log of our concentration, our nuclides in this case. On x, we have time. And if you take the slope, it will equal, in this case, negative the decay constant. So you take the slope of the line, it'll equal negative of the decay constant. This is also a first order graph. It is not the linear relationship here, but what we do see is as time goes by, we have a decrease in the concentration of whatever is decaying with time. Now, I will say that using these two equations are really important, and a lot of times, especially in this sort of radioactive decay situations, um, we oftentimes will use the half-life equation and the integrated rate law equation together. So a lot of times you may be given the half-life, so you could solve for the rate constant or decay constant and then put it into that equation. So very commonly you need to kind of use both of these equations together, and in a lot of cases you're using the half-life equation to get the decay constant, so then you could put it into your integrated rate law and solve for what you might be looking for in this particular case. Any questions on that there? So here are some half-lives and the types of decay that they undergo. And half-lives can be really fast, they can be really short, and they can be really, really long. So as you can see there, uranium-238, for example, is 4.5 times 10 to the 9 years. That's a half-life, by the way. So it takes that long for half of whatever you got to kind of go away. It's a super long time. None of us will be here after one half-life, I suppose. You can see some things are really, really fast, like TH219 there, 1.05 times 10 to minus 6 seconds. So just like that, pretty much it's gone as well. So some things can be really fast, some things can be really slow, depending on what you might be using it for. As you might talk about a little bit towards the end, obviously, you're doing something with medicine, you might want something on a lower end in terms of half-life. But a lot of stuff that we do use, for example, for fission type reactions, like uranium, has very, very long half-lives. And so does the stuff that is made as a result of those reactions have very, very long half-lives, which is some of the problems with using some of that stuff. So why don't you give this a go here? If you have a 1.35 milligram sample of plutonium 236, calculate the mass that will remain after 5 years. The half-life of Pu 236 is 2.86 years. Obviously, radioactive decay, we're going to roll with those two equations, which is really, again, our first order kinetics. And if you just want to use the regular sort of first order equations, that's fine. Or you can use the nuclear chemistry version of it, which is basically the same. And we have our half-life in this case, natural log of 2 over k. So in this case, we are looking for our final, which is this. Our initial is usually the guy with the little knot on the bottom there. And in this case, it's 1.35 milligrams. We have our time, and that's what the T does stand for there. By the way, that is time, not temperature, and that is 5 years. So we are missing the actual decay constant here to be able to solve for it, but we do have the half-life. So once again, we're going to have to use our half-life equation, and that means that our decay constant will be the natural log of 2 divided by our half-life. We'll put our natural log of 2 divided by 2.86 years. And that's going to get us here 0.242 reciprocal years. And if you remember, the units for a first order reaction in terms of the rate constant are, in this case, the decay constant is 1 over time, basically. So 1 over years is, or reciprocal years is really important. One of the other important things is when you do go into the integrated rate law here, that you do watch units between these two things. The decay constant unit of time and the time unit of time does need to be in the same unit. Otherwise, you will be off. In this case, they're both years, so we're good to go. We don't have to worry about that. So we now have everything that we need. A natural log of our final here going to equal the natural log of our initial, which is 1.35 milligrams, minus our decay constant of 0.242 reciprocal years times 2.8 years. Years will cancel, and that will leave us with milligrams when we're all said and done. So cleaning up the right-hand side there will give us the natural log of 1.35 minus 0.242 times 2.86. Going to get us the natural log of A is equal to minus 0.3920154-ish. Taking the E of both sides here, And hopefully we won't have any issues when we do this one. Hopefully not. There we go. And that's going to get me something like, I think, 0.676 here in this particular case. I feel like maybe I missed a number there. Hang on here. I did. I used 2.86 instead of 5 years there. Just didn't feel right to me. Sometimes, it just doesn't feel right. So let's try that again here. There we go. All right, let's use the right time there, which is actually 5. There we go. All right, take 2. All right, so natural log of 1.35 minus 0.242 times our time, which is 5 years, not our half-life. That's going to give us here minus 0.909895. Now we're going to E both sides there, and we're going to get 0.403, and these would be milligrams in this case. Sorry about that. Definitely want to use the time there. Any questions on that one there? It is less than we started with, which is good, right? If we went the wrong way there and go higher, that would not be good as it's decaying. So we should obviously end with less than we started with. Any questions on that there? All right. Take a look at another one here. All right, radon 222 is a gas suspected causing lung cancer. Assuming no loss or gain from leakage, if there is 10.24 grams of it today in the house, how much will be there in 5.4 weeks? Radon 222's half-life at 3.8 days. Let's see what you come up with there. Here, we're going to use our equation for first order here. We'll try to use the right numbers this time. That might be good. All right, let's see. All right, so in this case, we have there right now, which would be like initially, 10.24 grams. We want to know how much will be there after 5.4 weeks. That would be our final here. So once again, we are missing our decay constant, so we're going to use our half-life. Our half-life is actually in days, and our time is in weeks. So at some point, you do need to do a conversion so everybody's in the right units. It really doesn't matter which way you go, but you want to get everybody into sort of the same units. So we'll go with why not? We'll take weeks into days. So in 1 week, they say there's 7 days, so we'll go with that. So that's going to give me 5.4 times 7. It's going to give me an error. No, we're going to get 37.8 days. You obviously convert the half-life into weeks if you want to go that route as well. So with that, I'm going to leave my half-life in days and use my half-life equation to once again solve for my K. That's going to give me the natural log of 2, which is our 0.693, divided by 3.8 days. And that will get me 0.182, again, reciprocal days here. So now I have everything that I need. We're going to go again, our natural log of A will equal our natural log of our initial 10.24 minus our 0.182 reciprocal days. And we'll go with our actual time here of 37.8 days. In this case, days will cancel, and really grams is the only unit that will be left over. That means on the right-hand side here, natural log of 10.24 minus 0.182 times 37.8. Going to give us a natural log of A is equal to minus 4.553298. We're going to E both sides one more time for good measure. And we're going to end up with about 0.011 grams here should be left over at this point. Any questions on that calculation? So if you're still familiar with first order kinetics, or that kinetics calculation is pretty much the same calculation. Again, you could use any type of real unit for sort of the initial and final, as long as they're really, again, they're same unit on both sides. Any questions on that one there? Now, in addition to sort of this first order kinetics here, we could actually use this information as well to do something like radio dating and sort of figuring out how old something is. It's basically the same idea. There's radiocarbon dating where we use the half-life of carbon, which in this case is our carbon 14, 5730. I could also use uranium 238 dating, which decomposes into lead 206, and that half-life is 4.51 times 10 to the 9 years. So if we look at this sort of thing here, an ancient skull gives 4.5, and this is a rate of radioactive decay. This is disintegrations per minute per gram of carbon. So this is not Celsius, so that's per gram of carbon here. And it is a unit of radioactive decay. And a living organism gives 15.3 disintegrations per minute per gram of carbon. How old is the skull? So the importance of that per gram of carbon tells you we're using carbon's half-life here of 5730 is the one that we want to use here. So why don't you give that a go? And again, we'll use carbon's half-life there of 5730 years. And again, you could put those rates of radioactive decay into the equation, just like concentrations, grams, milligrams, just goes in the same way. Yeah. All right, so let's take a look again. We're going to go with our equation here. Actually, our two equations here. In this particular case, our final is the dead agent's gold. So that's going to be our final there, 4.5. Our initial is living, so 15.3. Living should probably have more counts than final there, right? As it's degrading over time or disintegrating over time. We are looking for how old it is. So in this case, we're actually looking for T. And once again, here we do need to use our half-life equation to get our decay constant. So we'll start there. Our K will equal natural log of 2 over the half-life, which is natural log of 2 in this case, using carbon as we have per gram of carbon, gives us a decay constant in this case of 0.000121 reciprocal years. With that, we could put in what we need here. Natural log of 4.5 equals the natural log of 15.3 minus our decay constant times T. For me personally, I go natural log of 15.3, then subtract it, natural log of 4.5 from it. So I end up doing this in terms of the math. So if you do that there, take a little natural log of 4.5 and minus the natural log of 15.3, that is going to get you there. Looks like negative 1.223775 equals negative Three zeros there. 1, 2, 3, 1, 2, 1 years equals t. We're going to divide this to the other side at this point, and we will end up with 0.000121 and end up with a t of 10,114 years. So pretty old. We could also round to about three significant figures, which is probably the right move there. So about 10,100 years would significant figure wise be probably what we're looking for. Any questions on that one here? All right, let's try another one here. Or actually, let's take a break and then we'll try another one here. So